Now I'll start by describing the question itself. So in this question, there is a diagram which looks something like this. Shows that there is a slit there, and there is a light. There's a light source, maybe a torchlight, and in front of this slit there's another screen with two slits. One slit there and one slit there. Two slits there, and some distance away there is a screen. Okay, so the light falls on the screen, and we are given that some fringes are observed. So these fringes, they are like sort of broad lines along here, looking something like this. One, two, three, 4, 5, 6, 7. Right, so that means if we imagine that we look at it, say from this side, let's say this is our eyes, this is our eye, and we look at it here, we'll see the pattern of light that we'll see here would look like this. Right. Okay. And we are given that this light has a wavelength of 600 nanometers. 600 nanometers, and we're given a few other things. We're given this distance. We're given that this distance here between the slits is is 0.4 millimeters, and the distance from the double slit to the screen is 2.5 meters. 2.5 meters from there to there. Okay, and the question is, what is the distance between this point, and this point? Okay, so between here and here. So that's all that the question tells us, between here and here. And yeah, and that's it really. So in order to do this question, we have to think about what we have learned or what we know about the double slit experiment. So since light is a wave, when light comes out from the two slits, the light would diffract. It will spread out from each of the slits like ripples on the ripple tank, and they would interfere. When they meet, they will interfere and give interference fringes and patterns like this. So at a certain point on the screen, for example, they will either interfere constructively or destructively. So if we imagine say a light ray from one slit and a light ray from the other slit meeting at the point on the screen, then they would interfere constructively with the path difference between this ray and this ray is a whole number of a wavelength. So if I imagine drawing a perpendicular from that slit here, this distance is roughly the path difference. So for constructive interference, this must be a full number of wavelengths, because only then will the crest from one slit meet the crest from the other slits, and they will add constructively to give a bright fringe. Okay, and the symbol we normally use for this distance is D, so I'll call that D, and for the spacing between slits, we call that A. So based on this relation, the idea is that we can make that there is a formula relating these quantities. Okay, and that formula is given based on the fact that this triangle here, and this bigger triangle there. Let me try and draw that as well. Okay, maybe I'll try and draw this, and this bigger triangle there, and there. Okay, that these two triangles are actually similar triangles. Okay, so if this distance is x, okay, so that's the important quantity here, because this distance would be directly related to the answer that we want to find. So this distance and this distance, okay, on this triangle can be related to the distances on this smaller triangle, because these two triangles are similar triangles. Then you know that ratios of the sides are equal for similar triangles, and that's how the formula that we normally learn, that's how it is obtained, that n lambda over a. Okay, let's write this down. N lambda, that means this side of the triangle divided by a, and this side is equal to this side divided by this side. Okay, so it all comes from similar triangles. But actually, to be very precise, I should really take this side divided by this longer side, because A is the longer side of this triangle. But one of the conditions for this double slit experiment is that the distance there is quite big, must be quite big compared to the fringe spacings. So because of that, this distance is approximately equal to the longest distance. So actually, the formula that we normally learn for Young's double slit is an approximate formula. Okay, because this distance is more direct to measure. We don't actually have to know the fringe spacing in order to measure this distance from screen to the slits. Okay, so once we have this, we need to, once we can remember this for this exam question, we need to think about how to find this spacing. Right, so x is the distance along this same direction, so they must be somehow related. But the tricky bit here is, the question did not actually say which of this fringe is at the center. Okay. And well, maybe we can kind of assume that the one at the center, the fringe at the center of this button is at the center. Okay, we can try that. So if that's the case, then I can say maybe the distance from there to there would be 1, 2, and 2.5. 2.5 fringes. Okay, and then I can just find x for n equals 2.5, and then multiply by 2. So that's one way to do it. So I can say that maybe that is the fringe, the central fringe, where n is 0. That's the fringe where n is 1. That's the fringe where n is 2. That one, n is 1. That one, n is 2, and so on. Right. So we can do that. There's a quick way actually, because if the distance x is quite small compared to this distance, then all the fringe spacings are very nearly equal. So all we really need to do is to count the number of fringe spacing over this distance. So that would be 1, 2, 3, 4, 5. So it's 5 fringe spacings. So it's like taking n, we can imagine taking n to be 5 and then calculating the x. So it'll be a bit like if we take n to be 5, what are we actually calculating? We're actually calculating the 5th fringe, aren't we? Meaning the one, if this is 2, then that's 3, and then that's another one 4, that's another one is 5. If I take n to be 5, I'm really calculating from this fringe, the 5th fringe to the center fringe. I'm really calculating this distance. But this distance will be the same as this distance, okay, as long as the x is quite small and then the spacings are quite equal. Right, so that's the same as x if I take n to be 5. So if we realize this, then we can reduce the step a bit. Yeah, all I need is to take n to be 5 and then find x. So finally, the thing to do is to make sure that we got all the numbers that we want. Okay, if I'm going to take n to be 5, we know lambda. Yes, we know lambda. Lambda is 600 nanometers. So we know lambda. Do we know A? Yes, it's 0.4 millimeters. D, 2.5. X, no, we don't. But that's what we want to find. Okay, so we're all set. We're all set. And now let me make X the subject. So X is equal to, okay, approximately equal to n lambda over A, D over the other side, n lambda D over A. Okay, and n, we have agreed that we'll take it as 5 lambda 600 nanometers, so that's 600 times 10 to the power of minus 9 meters. D 2.5 meters. D 2.5 meters. A is 0.4 millimeters. So 0.4 times 10 to the power of minus 3. So with all this, we can plug this into the calculator and get our answer. So the answer would be 0.01875 of a meter.